Hello and welcome back to Introductory Electromancy. Today we are continuing to build our transcranial direct current stimulation device, which enables you to place electrodes on your head and body to alter the operation of your brain. In the previous episode, I found that there was a broken link on the website, which I would usually use, but I was able to find the page it was supposed to link to by searching. So I guess these links have been reformatted and the site author has not updated them. In any case, this montage is supposed to link to a PDF of the study that was used in order to produce it. This was all better connected in the past because I wrote instructions for building the device I'm showing you in 2013. So in the 12 years since, there has been some link rot. Study. Okay, maybe. Okay, here we go. So now we can actually find out 32 participants is the number they used. And then have you got methods? Oh, you don't have full text. Oh, that's nice. Maybe if I search this with the string PDF, I'll be able to find the full text link. Here we go. Methods, participants, fluent English speakers, acknowledgements, references, no. These are still snippets. Okay. Promising. Just have to prove that I'm a human. Oh wow, discover the world's research. Okay, great. So I want to know how much current they're using and how long they ran. Okay, they used 1 milliamp for 20 minutes. This device, as designed, provides 2 because I figured why not go right up against the limit of the safety protocols defined at the University of Göttingen. But we're not even that far yet. I'm trying to analyze the circuit itself before I get into more practical application of it. So far, we have figured out this resistor, which protects the power indicator LED, dissipates 96.67 milliwatts. It's rated for 250. We should only run it up to 125. That's a safety factor of 2. I recommend derating all of your components by at least a safety factor of 2 for power, voltage, and current limits. The datasheet will give you a maximum current, maximum voltage, maximum power. Make sure that your design values are always half of that. This will improve the reliability and durability of the devices that you build. Now, the green LED will necessarily have the same current as the resistor because they are in series. So we can say that this I will equal 2.838 milliamps as well. Green LED is a standard 5 millimeter through-hole part. These things have a safe power dissipation limit of 100 milliwatts, 0.1 watts. Now, That means with a 50% derating factor, factor of 2, safety factor, however you want to put it, you should only run 0.05 watts through the device. The device should only be dissipating 0.05 watts or less. Less is fine. More is the problem. So, we know the current is 2.838 milliamps, so 0.002838 amps multiplied by the forward voltage, because again, power equals current times voltage. Forward voltage is known 1.94 volts. 1.94. So 0.0055 roughly. So power equals 0.0055 watts, which equals 5.5 milliwatts, which is much lower than the maximum rating of 100 milliwatts and the recommended safe rating of 50 milliwatts. So far, so good. We know that our LED and its current limiting resistor will operate properly within their safe power envelope. In the last episode, I talked about VI curves and how saying that a diode has a forward voltage of 0.7 volts is an approximation, because the actual current with respect to voltage of a diode is an exponential curve. Saying that it has a fixed forward voltage is equivalent to representing this curve as a straight line intersecting with another one at a 90-degree angle, saying no current flows until a certain threshold is reached, and then it allows infinite current to flow. For this circuit, because of the way that we're operating these diodes, a forward voltage drop of 0.66 volts is best to use for calculation. So we can move on to the next segment of the circuit, which is here. This supplies a voltage reference. Now this 36 volt supply, when the switch is closed, will be present across this circuit. This branch, this subsection of the circuit. I guess you'd call it a branch. So we know that there will be 36 volts here. We've defined this as ground, so this will be 0 volts. These diodes will each burn 0.66 volts each. And I'm ignoring this connection here for now because the current through it is negligible for the analysis of this circuit. So this whole package of diodes will have a voltage drop of 3 times 0.66 volts. .98 volts total. So 1.98 volts across all 3 diodes. And since we know that 36 volts is going to be supplied, then the voltage across the resistor here will have to be the 36 volt supply minus 1.98 volts, which is 34.02 volts. Now, we could calculate the current through the resistor using Ohm's law, then multiply that current by the voltage in order to figure out the power dissipated by the resistor. But let's use an alternate form of the power law, which was demonstrated in either the first or second episode, I don't remember which. P equals V squared over R. This is from algebraic substitution of Ohm's law into the power law. In either case, we now know the voltage across the resistor, 34.02 volts. So that value squared, the value of the resistor itself is 12 kiloohms, 12,000 ohms. So this will give us the power dissipation of that resistor. .0964 rounded. 0.0964 watts, which equals 9. Mistakes. 96.4 milliwatts. This resistor is rated for 250 milliwatts, which means for safety's sake you want to run it at 125 milliwatts or less. 96.4 milliwatts is indeed less than 125. So that resistor won't explode. The current through here will be very similar to the current through here. So roughly 2.8 milliamps, very roughly. The reason I bring this up, 2.8 milliamps, ignoring the current through this branch, would be flowing through these diodes. These diodes are rated for an amp. So they can handle 2.8 thousandths of an amp very well. We do not need to worry about that. So the diodes won't blow up. The resistor won't blow up. We could calculate the power dissipation of the diodes, but it is so far below their rated power, we don't even need to know the exact value. So we can skip that for now. The important thing is that we're guaranteeing that 1.98 volts will be present here at this node. And then we get to our tip 31C. It's an NPN transistor. There are various approximations that you can use for the NPN transistor. Running out of paper. I mean, I have plenty of paper. I'm running out of space on the paper that I'm using. So, an NPN transistor, we can make a simplified model for it for the purposes of circuit analysis. And that simplified model is a diode and then a current-controlled current source. So we can say that our transistor acts like it has a diode between the base and emitter with some current flowing through it. Let's call it I sub D. And then this here will be beta or HFE times I sub D. And then we're using a tip 31C transistor. What is its beta value? Various beta values are available. They say that the beta value for this transistor will be somewhere between 25 and 50. This is a value that changes depending on how much collector current is flowing. It's going to be nowhere near an amp even. Nowhere near 3 amps. It'll be 0.02 of an amp. So let's use the value of 50. And we can get even further than that in our simplification. Looking back at our original schematic, I said that the current flow through this branch is negligible. In analyzing this circuit, we don't need to worry too much about it. The important thing we have to bear in mind is that there will be a diode voltage drop required to turn on the transistor. And while it's typically 0.7 volts, that 0.7 volts is actually a simplification. And in this circuit, it's a lot easier just to assume the value is 0.66 volts. So there are 1.98 volts here from the action of this voltage regulator, we'll call it. 1.98 volts, then 0.66 volts gets burned off by the base emitter junction, which means that the voltage value here will be 1.98 minus 0.66. .32 volts. So 1.32 volts is at this point here. And an important thing to note, if you have two resistors in series, their values simply add. This is equivalent to, very badly drawn arrow, this is equivalent to a single resistor whose value is the sum of these two, so it would be 660 ohms. That's important because then we can calculate from this voltage here what the total current flow through this little part of the circuit is. It'll be this voltage, 1.32 volts, over 660 ohms, equals 0.002 amps, equals 2 milliamps. So 2 milliamps will flow through this leg of the circuit. This transistor in this application will have a beta of about 50, a current gain of about 50. What this means is that some current will flow into the base of the transistor, and then 50 times that current will flow into the collector. And so the base current is small enough that we can ignore it in this application and say that this current must be the same as the current flowing out, which we already know is 2 milliamps, so this must also be 2 milliamps. There will be a 2% error if the transistor has a beta of 50 in making this assumption, but a 2% error is not a big deal in this circuit because these resistors are all they're accurate to within 5%. The band on the far right is gold. This one is brown, black, brown, gold. So it is 1, 0, and then another 0 after that. And the gold means plus or minus 5%. So if the resistors aren't even accurate to 5%, a 2% error does not make much difference. And we can build it and test it. Now, these two additional resistors, they are here for safety purposes. In case there is some sort of error and this transistor becomes shorted, these resistors will keep the current flowing through your brain to a safe level. Not safe according to the University of Göttingen standards. I mean, much better than the alternative. And you would know if that happened. I think I've built about 50 of these and sent them all over the world. I have not received any reports of them failing, but know that there are multiple redundant safety measures in case that does happen, built into this circuit. That doesn't mean that you should leave them out to make your life easier. Include them. You only get one brain until you can figure out how to build yourself a replacement and or attach it to your existing one. But that's the long and short of it from a circuit analysis perspective. We could spend a lot longer calculating the power dissipation of each component. And if you want me to comment it, I will. But in this case, it's not really necessary. This thing is good for up to 40 watts of power dissipation. You cannot get 40 watts out of 4 9-volt batteries, at least not for long periods. And then power dissipation at this resistor will be I squared R. So if we know the current is 2 milliamps and the resistor is 2.2 kiloohms, then we can very quickly calculate and make sure that it is within the safe power envelope. There's more detail to all of this, but I don't really want to overwhelm you with it. I'm trying to cover it as it comes up in a practical project. Okay. Yeah. I'm doing my math wrong. I entered division instead of multiplication here. That's not good. That looks more right. 8.8 milliwatts. 8.8 milliwatts is below the 250 milliwatts that these resistors are rated at, and still below the 125 milliwatts, which would be the safe operating area with a safety factor of 2. You want a safety factor of 2 in electronics. Alternatively put, derate everything by 50%. 8.8 milliwatts, which is the same as 0.0088 watts. Exciting stuff, I know. Okay, so you can build this circuit and use it to begin your assembly of your brainwashing cult, or neuromodulation cooperative. The team of people you pull together to try and save the world and all that. This can help you enhance them. There are various other things that you could use, such as oxiracetam with choline bitartrate and cytidine diphosphate choline. And I mean, there are shorter term effect ones like huperzine A or adrafinil or phenylpiracetam, but that's outside the scope of this current video. If you want to hear more about them, comment, and I will try to include all of the information on making yourself into a superhuman cyborg that I have available.